This is our presentation on optimizing dark channel prior and some innovative approaches to image dehazing. I'm Maggie Boyd.
I am Becca Hecht.
I am Alexis Duran.
And I'm Aiden Hammer.
So just a quick overview of all the things that we did in our project. We are trying to figure out how can we optimize the computational efficiency of dehazing algorithms. Some things that we did with our methods, we used dark channel prior and some other supplemental computational techniques as well. Some of our key findings were optimizing DCP using MATLAB and Python code as well. And the impact of this project overall is being able to quickly and effectively dehaze images for different applications. So our motivation for this project. First of all, let's talk about what specifically dehazing is. Dehazing is enhancing the clarity of an image by removing haze. Some causes of this haze could be dust, smoke, fog, and other small particles that could scatter light in the air. And this is important because dehazing can help increase visibility and it can help identify objects in an image, as you can see in this autonomous driving application photo right here. That's being able to identify all of those different things in the image so that the car is not hitting things that it isn't supposed to. Then obviously also for safety and security applications, we could talk about security cameras, things like that, and also overall image restoration and enhancement. So first of all, we're going to talk about the atmospheric scattering model. This is the mathematical model that we use for dehazing. It's kind of described as the haze model rather than the dehaze model, which we'll explain a little bit later. But essentially, I of X is the observed image or the hazy image that you can see in this photo on the right. And then J of X is the seen radiance, which is the photo with no haze, which you can see on the left in this photo. T of X is the transmission map, which is the amount of light that is not scattered in the image. This is a number from 0 to 1. And T of X can be represented as e to the negative beta times D of X, where beta is the scattering coefficient, which is kind of described as the density of the haze within the image. And D is the depth, so the distance that the camera is away from the scene. And A is the global atmospheric light, which is that white light that you see in the image on the right. And this is just a photo showing all of the different things. You can see the scattering off of all of the different particles in the air. You can see that density or the scattering coefficient of all of the haze in the image. You can see the distance from the camera, all of these different things interacting together, which is then causing that haze in the photo. And this is how we turn our haze model or the atmospheric scattering model into a dehazing model. So essentially, because J of X is the clear image, we're trying to take all of these different elements out of J of X. So we're trying to derive the clear image from all of these different elements. And to do this, we essentially kind of solve for J of X in the equation. It's pretty simple math. And so we have J of X equals I of X minus A divided by T of X plus A. And what happens with this is because now T of X is in the denominator, that's actually making a very unstable equation. It can cause a lot of instability in this application. So what we do is we add a maximization function in the denominator where we have T of X, max T of X comma T0. And this is just making sure that the equation is not dividing too close to 0, where it's going to start causing problems in that equation.
So the method that we are using to dehaze specifically is the dark channel prior method. This method is essentially using the dark channel to solve for a dehazed image. So as you can see, the way finding a dark channel works is taking a small patch of pixels called a local patch and separating it out, as you can see, into its 3 distinct color channels. In this specific example, you'd see that the darkest patch, and as far as values go, is the B channel. So it would take the smallest value from the patch in the B channel and take that value and put it into that local patch and turn the entire local patch that color. So this is just a visualization of the way dark channel prior works. This is an estimation of the dark channel, a visualization of it. So essentially what it is, you can see all of the little boxes that are created in the graphic. That's just showing how the little local patches are made. this is actually one of the shortcomings of dark channel prior, because when the dark channel is implemented back into the image, it can create some pixelization and often creates unnecessary artifacts in the image that weren't there in the first place.
So dark channel prior has 4 steps. We first start off with our hazy image, our I of X, and we then hand it off to the dark channel prior algorithm. So in here you can see the image has turned into like a grayscale image, and as you'll see later on, there's patch sizes. So the objects in the foreground and the background may be pixelated to a certain extent depending on the patch size. But here it is essentially a two-dimensional matrix with just color data and positional values. Our second step would be estimating the atmospheric light, and this is done through done through the dark channel estimation, but instead of getting the darkest pixels possible, we're getting the top 0.1% of lightest pixels. And this can vary the 0.1 or 0.2% of lightest pixels depending on your application. And as you can see here in step 3 with the transmission map equation, we are estimating the transmission map by getting the atmospheric light and the dark channel and getting the amount of basically the light that's getting to the camera. And lastly, step 4, we end up with our dehazed image, which is J of X, and the scene radiance is recovered. And compared to the original image, the haze is removed to a certain extent, but not all haze can be removed. So here we have our transmission map estimation. It is given by the equation T of X equals 1 minus omega times J of dark over A. So T of X is a matrix with all values being between 0 and 1, so they're going to be floating point numbers or decimal point numbers. And it represents the amount of light that reaches the camera without being scattered by haze, which is just anything like fog or just particles in the air that are scattering light. So any light that isn't reflected off those particles that reaches the camera. And omega is our constant parameter, which is typically set to 0.95. And this is also a value that ranges between, it has to be greater than 0 and less than 1. Typically, you see it at 0.95, but again, this also can be changed varying on the situation. So if you're doing applications where there's a horizon, you typically keep it at 0.95, whereas if you're doing just bird's eye view down, you might set it to typically a different value. So we'll see here shortly, if omega is set too high, it could lead to oversaturation of the image and an overall loss of detail. And the same could be said if omega is set too low, it won't remove much of the haze and you won't see much of the haze removal. And here we can see the effects of the haze removal parameter. Here we have on the left, omega being 0.6, and the image is still rather hazy in comparison to the original image. Here with the center image being 0.95, you can see that there's still haze is removed, and there's a little bit of saturation added back to the image, and there's a bit of more clarity. And on the last image on the right, with omega being anything greater than 1.0, we'll see that it just becomes oversaturated and you lose a lot of detail in the image.
So in order to use this equation, we have to discretize it. So discretizing is essentially taking an equation from its continuous form, just using x's and y's, and turning it into a form that can be used for applications in things like coding and images and things like that. So essentially what we're doing is turning the continuous forms x and y into points of a matrix. So what we have is x is going to be ij, the specific pixels on the hazed image, and then y is going to be I prime j prime, which is going to be other pixels on the matrix. So broken down, the ij, as was the x before, are the coordinates of the center pixel of the local patch. Then we have I prime j prime, which are the coordinates of the darkest pixel in the image in that little local patch. Then the omega of ij is the local patch itself. Which is centered around that ij, as I said before. And this is also typically a 15 by 15 patch, although this does tend to change, as we're going to hear about later. Then the JC of I prime J prime is the intensity value of that darkest pixel I prime J prime. So as I said before, this intensity value then gets plugged in as the local patch values. The entire local patch becomes that new pixel value.
So dark channel prior has strengths and limitations. Some of the strengths of dark channel prior is that it's quick and efficient for single image dehazing. The code in the process is relatively simple compared to other longer and more higher computational cost algorithms. And it's relatively quick and it does the job of dehazing on single images. Some of the limitations are like Becca mentioned earlier, there could be some artifacts as we can kind of see in like the sky and the brush area when after the dark channel prior is used to dehaze, some artifacts that weren't there do appear, and there tends to be sometimes an oversaturation on the final image. So the image quality is still left up to future work, and so we're going to discuss better ways that we try to optimize dark channel prior, but we have found it works well for dehazing. And so some of the challenges and limitations that we found was here we can see on MATLAB and Python, there's kind of that haloing effect that happens in the sky around objects where there wasn't already haze or I'm sorry, a halo. So the quality of the photo is probably one of the bigger limitations that we focused on optimizing, and we also focused on optimizing runtime, which we'll also get into in future slides. So the first thing we thought was, how do we make this process faster and how can we process multiple images at once? So we found a parallel processing toolkit that's already built into MATLAB is where we ran this code. And parallel processing was helpful and efficient in speeding up the process of single image dehazing and also giving us the ability to dehaze multiple images at once. While we expected we expected that there would be no quality change in the photos before and after dehazing, we can still see here that this is with the parallel processing feature. And we still do get those artifacts in the sky, especially around brushes and skylines. But we did find in the data that the parallel processing features did help in images that are a little bit smaller. And we can see here on the table, this was done by us. This was our experimental time using the 3 images shown on the previous slide. We found that with the smaller images, the time saved was substantial compared to the larger images. And so while higher resolution images showed the most improvement, they're definitely faster than dark channel prior. So the image 1 and image 3 showed almost 60 and almost 50% time saved compared to image 2 was only about 13%. So while the smaller images were more effective and quicker processing time, we would look at future work to figure out why the image 2, the larger image, processed a little bit slower than the smaller images. And then here's just some look ahead into future work that we can look into when it comes to dehazing. So the real-world applications is dehazing can be used to enhance visibility in foggy or hazy conditions, and it boosts drone performance. So when we're thinking of drones using in emergency situations such as fires or natural disasters and things like that, and it's crucial for emergencies and object detection. And what's next in our work that we can look forward to is machine learning, smarter algorithms to adapt to new environments, visibility, and efficiency to optimize computational efficiency for real-time use.
We would like to thank Dr. Raquel Lopez for her invaluable mentorship, guidance, and ongoing support throughout this entire research process. We would also like to thank our entire team just for our collaborative efforts and hard work and commitment, which made all of this research possible. We would like to give a special thanks to Dr. Malena Español and the ASU research team that partnered with us to create this project. And we were also funded by the Center for Undergraduate Research in Mathematics, or CURM program. And if you would like to look into our Python and MATLAB, we have our repositories and QR codes here that are welcome for you to scan. Thank you, everybody, for listening.